নীলকমল ইতিমধ্যে তোমাৰ স্ক্ৰীনখন শ্বেয়াৰ কৰি থৈ দিয়া নেকি দেৱজিত ভাল হ'ব চাগে
মই কৰিছো
নীলকমল তুমি আৰম্ভ কৰিব পাৰা এতিয়া পাৰিবা সৰি
Hello, can you unmute?
এতিয়া পাৰিবা তুমি শুনিছো কৰা প্লিজ
মোৰ মাতটো ইকো হৈছে নেকি?
নাই হোৱা প্লিজ go ahead
Okay. So welcome all of you for this today's session on Nobel Prize in Chemistry 2025. So it will be delivered by Professor Debajit Sarma from Department of Chemistry, IIT Patna. Debajit Sarma received his MSc from the Indian Institute of Technology, Delhi in 2006 and PhD from Indian Institute of Science, Bangalore in 2012. Before that, he did his bachelor's at B. Borua College, Guwahati. He was a postdoctoral fellow at Northwestern University from 2013 to 2016, Illinois, with Professor Mercury Kanajatis before joining the Department of Chemistry of IIT Patna in 2017. He is currently an associate professor at IIT Patna, and his current research includes inorganic materials for sensing, catalysis, energy conversion, and environmental remediation. So today he is going to talk about the metal organic framework that received the Nobel Prize in 2025 by Professor Yaghi and his colleagues. And the stage is set for Dr. Debajit Sarma to take over. And you can please share the slides and start the lecture, please.
মই অলৰেডি স্লাইড শ্বেয়াৰ কৰিছো ভিজিবল হৈছে নে হোৱা নাই বা
হৈছে
ভিজিবল হৈছে না হয় সো ধন্যবাদ নীলকমল থ্যাংক ইউ পোনপ্ৰথমে মই 15 মিনিট শিক্ষাৰ লগত জড়িত সকলো বিষয়ববীয়া আৰু সদস্যলৈ মোৰ আন্তৰিক শ্ৰদ্ধা জ্ঞাপন কৰিছো আৰু লগতে আজিৰ এই আলোচনা চক্ৰলৈ মই সকলোকে স্বাগতম জনাইছো সো আজি মই আপোনালোকক এই বছৰৰ ৰসায়ন যোৱা বছৰ আসলতে 2025 ত ৰসায়ন বিজ্ঞানৰ নোবেল প্ৰাইজ বিজয়ী বৈজ্ঞানিক আৰু বিষয়ৰ ওপৰত অকমান চমু বিৱৰণ দিবলৈ চেষ্টা কৰিম। মই মাজে মাজে অসমীয়া কম আমাৰ ছাত্ৰ ছাত্ৰীৰ সুবিধাৰ্থে, আৰু শ্লাইডত বেছিভাগ ডেছক্ৰিপশ্যন তাৰমানে আপোনাৰ ইংলিছতেই থাকিব। চ' আৰম্ভণিতেই মোৰ বিষয়ে অলৰেডি নীলকমলে ক'লেই গোটেইখিনি। চ' মই মোৰ ঘৰ বশিষ্ঠ গুৱাহাটীত। মই দিছপুৰ চৰকাৰী উচ্চতৰ মাধ্যমিক বিদ্যালয়ৰ পৰা 1999 চনত HSLC উত্তীৰ্ণ হৈছিলোঁ। তাৰপিছত মই বিবৰুৱা কলেজত HS আৰু BSc কেমিষ্ট্ৰি মেজৰ। তাৰপিছত আপোনাৰ IIT দিল্লীৰ পৰা মই MSc কৰিলোঁ, আৰু ভাৰতীয় বিজ্ঞান প্ৰতিষ্ঠান ISCৰ SSCU ডিপাৰ্টমেণ্টৰ পৰা PhD। PhD কৰি মই 4 বছৰ নৰ্থ ইষ্টাৰ্ণ ইউনিভাৰ্চিটিত প্ৰফেচাৰ মাৰ্গাৰী কানাজিটিছৰ লগত পোষ্ট ডক্টৰেট গৱেষণা কৰি আছিলোঁ, আৰু তাৰপিছত 2017 জানুৱাৰীত মই IIT পাটনাৰ কেমিষ্ট্ৰি ডিপাৰ্টমেণ্টত সহকাৰী অধ্যাপক হিচাপে জইন কৰিছিলোঁ, আৰু এতিয়া মই এজন সহযোগী অধ্যাপক কেমিষ্ট্ৰি ডিপাৰ্টমেণ্টত। এই বছৰৰ মানে যোৱা 2025ৰ নবেল প্ৰাইজ ৰসায়ন বিজ্ঞানত দিয়া হৈছিলে ফৰ দ্য ডেভেলপমেণ্ট অফ মেটেল অৰ্গেনিক ফ্ৰেমৱৰ্ক। আমি আলোচনা কৰিম মেটেল অৰ্গেনিক ফ্ৰেমৱৰ্ক কি, ইয়াৰ প্ৰয়োজনীয়তা, আৰু কেনেকৈ ই আমাৰ দৈনন্দিন জীৱনত আমাক সহায় কৰিব পাৰে, তাৰ বিষয়ে আমি কিছু চমু আভাস আজিৰ এই আলোচনাত ডিছকাছ কৰিম। চ' বিশেষকৈ 3জন চাইণ্টিষ্টক ৰসায়ন বিজ্ঞানৰ নবেল প্ৰাইজ দিয়া হ'ল যোৱা বছৰ। তেওঁলোক হ'ল প্ৰফেচাৰ চুচুমু কিটাগাৱা। তেখেত জাপানত কাৰ্যৰত। তেওঁ 1951ত কয়টত জন্ম হৈছিলে। এতিয়াও তেওঁ কয়ট ইউনিভাৰ্চিটিতে এজন প্ৰফেচাৰ। নেক্সট ৰিচাৰ্ড ৰবচন। তেওঁৰ জন্ম ইউকেত। তেখেতে PhD 1960। তাৰপিছত তেখেতে কৰ্মজীৱনত ইউনিভাৰ্চিটি অফ মেলবৰ্ণ অষ্ট্ৰেলিয়াত কৰ্মৰত। এজন হ'ল ওমৰ য়াগি। তেওঁ 1965ত জন্ম জৰ্ডানত, আৰু তেখেতে PhD ইউনিভাৰ্চিটি অফ ইলিনয় আৰ্বানা চেম্পেইনৰ পৰা PhD লয়, আৰু তেখেত বৰ্তমান ইউনিভাৰ্চিটি অফ কেলিফৰ্ণিয়া বাৰ্কলিত প্ৰফেচাৰ। চ' এই 3জন বৈজ্ঞানিককে প্ৰফেচাৰ কিটাগাৱা, প্ৰফেচাৰ ৰবচন আৰু ওমৰ য়াগিক সংযুক্তভাৱে যোৱা বছৰৰ ৰসায়ন বিজ্ঞানৰ নবেল প্ৰাইজ দিয়া হয়। চ' আমি যদি চাওঁ মেটেল অৰ্গেনিক ফ্ৰেমৱৰ্ক, মানে নবেল প্ৰাইজ দিয়া প্ৰেছ বিজ্ঞপ্তিখনত কোৱা আছে যে ফৰ দ্য ডেভেলপমেণ্ট অফ মেটেল অৰ্গেনিক ফ্ৰেমৱৰ্ক, গোটেই এৰিয়াটো ডেভেলপ কৰাৰ কাৰণে তেওঁলোকক নবেল প্ৰাইজৰ কাৰণে নবেল প্ৰাইজ দিয়া হয়। যদি আমি তাৰ অসমীয়া ট্ৰান্সলেশ্যন বিচাৰো, সেয়া হ'ল ধাতু মানে আমাৰ মেটেল, জৈৱিক অৰ্গেনিক লিংকাৰৰ গাঁথনি বা ফ্ৰেমৱৰ্কৰ উন্নয়নৰ বাবে। চ' আমি খুব সংক্ষিপ্তে যদি আমি চাব যাওঁ, এয়া আচলতে এক মেটেল আয়ন বা মেটেল আয়নৰ এটা গ্ৰুপ অফ মেটেল আয়নক যদি আমি এটা অৰ্গেনিক লিংকাৰেৰে জইন কৰোঁ, তেতিয়া আমি যদি এটা এনেকুৱা ফ্ৰেমৱৰ্ক তৈয়াৰী কৰিব পাৰোঁ, তো বেচিকেলি তেনেকুৱা ধৰণৰ কম্পাউণ্ডবোৰক মেটেল অৰ্গেনিক ফ্ৰেমৱৰ্ক বুলি কোৱা হয়। ইয়াৰ এটা ডাঙৰ বৈশিষ্ট্য হ'ল যে যেতিয়া এই ফ্ৰেমৱৰ্ক সৃষ্টি হয়, এই ফ্ৰেমৱৰ্ক অকল এটা মলেকুলাৰ লেভেলত নাথাকি ই এটা পলিমাৰিক ষ্ট্ৰাকচাৰ তৈয়াৰী কৰে। So it can be in 1 dimension, it can be in a 2 dimension, as well as it can grow one above the other in a repetitive manner, repetitive and precise manner to give a three-dimensional framework structure. সেই কাৰণে নামটো ফ্ৰেমৱৰ্কটো ইয়াৰ পৰা আহিছে। So যদি আমি বেসিক কনস্টিটিউয়েন্টৰ কথা ভাবো, ইয়াত মেটেল আয়ন বা আয়নসমূহ থাকে। এই মেটেল আয়ন বা আয়নসমূহক এটা কানেক্টৰ বা অৰ্গেনিক লিংকাৰেৰে we can connect them to form এটা framework structure. So that is the basic idea about of a metal organic framework. এই কাৰ্টুনটো আপোনাৰ প্ৰেছ বিজ্ঞপ্তিৰ পৰা লোৱা হৈছে, নোবেল প্ৰাইজ প্ৰেছ বিজ্ঞপ্তিৰ পৰা। ইয়াতে কোৱা আছে MOF is a revolutionary class of porous material with enormous internal surface area. ইয়াৰ সবতছে ডাঙৰ বৈশিষ্ট্য হৈছে যে this material possesses extremely high surface area and that gives them a very unique property. First, they are crystalline as well as they have this very high internal surface area. আপোনালোকে চাব পাৰে যে এই পাৰ্টিকুলাৰ স্কিমেটিক্সত আমি চাও যে তাৰ ভিতৰত ইমান স্পেচ আছে যে সেই স্পেচটো ইউটিলাইজ কৰি আমি তাতে বিভিন্ন ধৰণৰ ৰিয়েকশন কৰিব পাৰো, বা এই স্পেচটো বা স্পেচৰ ভিতৰত থকা সাৰফেসৰ ফাংশনাল গ্ৰুপবোৰ লৈ আমি তাত বিভিন্ন ধৰণৰ ৰিয়েকশন কৰিব পাৰো। So এয়া আপোনাৰ just basic idea of metal organic framework. So আমি যদি metal organic framework or development to চাও, কেনেকে metal organic framework last 40 বছৰত আৰম্ভণিৰ পৰা আজিৰ এই অৱস্থা পাইছে, তেনেহলে আমি ইয়াৰ প্ৰিভিয়াস ইনস্পিৰেশনবোৰ চাব লাগিব। তো যেতিয়াই আমি কোনোবা ষ্ট্ৰাকচাৰৰ কথা কওঁ, আমাৰ সকলোৱে স্কুলৰ দিনত পঢ়ি অহা ষ্ট্ৰাকচাৰবোৰৰ কথা মনত পৰে। যেনেকুৱাকে আমি সবেই জানো মিথেনৰ ষ্ট্ৰাকচাৰ। মিথেনৰ ষ্ট্ৰাকচাৰত এটা কাৰ্বন 4টা হাইড্ৰোজেনৰ লগত সংযুক্ত। It is connected with 4 hydrogen to give it a tetrahedral structure. So in the tetrahedral structure, we can see that, the carbon connect with all the 4 hydrogen, and each of this hydrogen carbon hydrogen angle is 109 degree 0.5 minute. Now these structures are molecular structure. এইবোৰ molecular structure। এটা CH4 molecule আৰু এটা CH4 moleculeৰ মাজত কোনো কানেকশন নাই। তেওঁলোকৰ মাজত কিছুমান there might be some interactions, but they are not connected to each other. Next, আমি যদি চাও, আমি বেনজিন মলিকুলৰ কথা মনত পেলাব পাৰো। বেনজিন মলিকুল এটা প্লেনাৰ মলিকুল, য'ত কাৰ্বন এটা কাৰ্বন আৰু এটা কাৰ্বনৰ লগত সংযুক্ত, কিন্তু ইয়াতে কাৰ্বনবোৰ তেনেকুৱা টেট্ৰাহেড্ৰেল কাৰ্বন নহয়, প্লেনাৰ কাৰ্বন হয় because of their hybridization. So তেওঁলোক এটা কাৰ্বন তিনিটা অন্য এটমৰ লগত কানেক্টেড, তেনেকুৱাকে ইয়াতে দুটা কাৰ্বন আৰু এটা হাইড্ৰোজেনৰ লগত কানেক্টেড। এইবিলাক এটা মলিকুলাৰ ষ্ট্ৰাকচাৰ। ইয়াৰ পিছত আমি এই ষ্ট্ৰাকচাৰৰ পৰা নেক্সট 20 শতিকাৰ আৰম্ভণিত আমি কোঅৰ্ডিনেশন কম্পাউণ্ডৰ কথা শুনিব পাওঁ, য'ত আলফ্ৰেড ৱাৰ্নাৰে ৱাৰ্নাৰ থিয়ৰী দিয়ে। ৱাৰ্নাৰ থিয়ৰীত তেখেতে বিভিন্ন ধৰণৰ কোঅৰ্ডিনেশন কম্পাউণ্ডৰ কথা কয়। কোঅৰ্ডিনেশন কম্পাউণ্ড হল য'ত আমি কোনো ধাতৱীয় আয়ন বা মেটেল আয়ন, যদি কোনোবা এটা লিগেন ৱাটাৰ মলিকিউল হ'ব পাৰে বা বিভিন্ন ধৰণৰ অন্য এমোনিয়া হ'ব পাৰে, য'ত এটা ইলেক্ট্ৰন পেয়াৰ থাকিলে ইলেক্ট্ৰন পেয়াৰটো মেটেলক ডোনেট কৰি এটা কোঅৰ্ডিনেট কোভেলেন্ট বন্ড বনালে, সেইটো কাৰণে ইহঁতক কোঅৰ্ডিনেশন কম্পাউণ্ড বুলি কোৱা হয়। সো এয়া আপোনাৰ আৰম্ভণিৰ স্ট্ৰাকচাৰেল কেমিষ্ট্ৰিৰ কথা ক'লে আমি এই কম্পাউণ্ডবোৰৰ কথা ক'ব পাৰো। After that, when we talk about extended structure কথা ক'লে next example আমাৰ মনলৈ আহিব পাৰে, আমি ইংকত ইউজ কৰো প্ৰুচিয়ান ব্লু কালাৰ ইংক। প্ৰুচিয়ান ব্লু কালাৰ ইংকত it's also a coordination compound of iron, কিন্তু ইয়াত one of the iron is connected to a nitrogen of a cyano group, and the carbon is connected to another iron ion. সেইটো কাৰণে কি হয়, এই সাইনাইড গ্ৰুপটো এটা কানেক্টৰ হিচাপত কাম কৰে দুটা আইৰন এটমৰ মাজত, আৰু ই এটা এক্সটেন্ডেড স্ট্ৰাকচাৰ দিয়ে টু দ্য প্ৰুচিয়ান গ্লু. So a Prussian glue is well known from 18th century. Their structure has come into known in and around 1950 or so, when X-ray crystallography has been developed. So আমি যদি আর্লি স্ট্রাকচাৰৰ কথা চাব যাওঁ, য'ত এটা পলিমাৰিক স্ট্ৰাকচাৰৰ কানেকশ্যনৰ কথা কওঁ, তেনেহ'লে আমি প্ৰুচিয়ান গ্লুৰ কথা ক'ব পাৰোঁ. ইয়া হওক আমাৰ প্ৰথম বৈজ্ঞানিক ৰবছনৰ ওপৰত. So Professor Robson, Richard Robson, তেখেতে আপোনাৰ University of Melbourne solid state chemistry পঢ়াইছিলে. So he used to teach solid state chemistry. In the solid state chemistry, he used to teach the structure using this ball and stick model. মই এক অকমান সময়ৰ কাৰণে স্ক্ৰীনখন পৰা আপোনালোকক মডেল এটা দেখুৱাব বিচাৰিম. ভালকে মোক দেখিব পাৰিছে নহয়? সো ইয়াতে যদি আপুনি তেখেতে যেতিয়া ক্লাছ পঢ়াবলৈ যায়, ক্লাছত পঢ়াবলৈ যাওঁতে তেখেতে এই এনেকুৱা আজিকালি কিনিব পায়, আপোনালোকে দেখিছে চাগে স্কুলৰ দিনত, এনেকুৱা ধৰণৰ প্লাষ্টিকৰ বল এণ্ড ষ্টিক মডেল কিনিব পায়. তেতিয়া আগতে তেনেকুৱা কিনিব পোৱা নাছিলে, কিন্তু তেখেতে কি কৰিছিলে, তেখেতে কাঠৰ এনেকুৱা কিছুমান বল ক্ৰিয়েট কৰিছিলে. So he used to make some wooden ball with the help of the carpenter, and he asked the carpenter to precisely put some holes in the carbon molecule so that he can put the stick there, and then when he goes to the class, so he can show different types of structure that he has formed, that he can show. So he used to show them a diamond structure. তেখেতে ক্লাছত গৈ পেলাই এনেকুৱা ধৰণৰ ডায়মণ্ড ষ্ট্ৰাকচাৰ এটা বুজাইছিলে গোটেই ক্লাছত. এইটো এটা ডায়মণ্ড ষ্ট্ৰাকচাৰ. ইয়াতে যদি চাই, এই কাৰ্বনটো যদি চাই, এই কাৰ্বনটো 4টা আৰু ডিফাৰেণ্ট কাৰ্বন এটমৰ লগত কানেক্টেড. So এই ষ্ট্ৰাকচাৰটো যদি আমি 3 ডাইমেনশ্যনত ভাবিব বিচাৰো, that will become a diamond structure. So তেখেতে যেতিয়া ক্লাছত এনেকুৱাকে ডায়মণ্ড ষ্ট্ৰাকচাৰ বুজাই আছিলে, বছৰৰ পিছত বছৰ, 4 বছৰ 5 বছৰ, so তেখেতে ভাবিব আৰম্ভ কৰিলে আমি কেনেবাকে এই কাৰ্বনবোৰ যে কানেক্ট হৈ আছে 4টা কাৰ্বনৰ লগত, this carbon is connected with 4 carbon, which is a tetrahedral carbon. Can we replace this carbon with something else, keeping this tetrahedral arrangement similar? Or can we replace this connector, which is simply a bond, by a longer connector? So that is the origin of idea of this entire area of metal organic framework. So তেখেতে কি কৰিলে, তেখেতে এই কাৰ্বন এটম এটা লৈ, এইটো এটা কাৰ্বন এটম, এই কাৰ্বন এটমৰ চাৰিওকাষে এনেকুৱা ধৰণৰ এটা বেনজিন মলিকুলৰ কথা চিন্তা কৰিলে, আৰু তাৰ লগত এই প্ৰুচিয়ান গ্লুৰ সাইনাইড গ্ৰুপটোৰ কথা চিন্তা কৰিলে. তেখেতে ভাবিলে যদি মই এনেকুৱাকে এটা কাৰ্বনত এনেকুৱাকে এটা বেনজিন ৰিং দি ইয়াতে যদি আমি এটা সায়ানো গ্ৰুপ লগাব পাৰো, তেনেহ'লে চাগে এই নাইট্ৰজেনটো আমি এটা মেটেলৰ লগত কানেক্ট কৰিব পাৰিম. ইফালৰ পৰা আৰু এটা গৈ তেনেকে কানেক্ট হ'ব, এইটো সাইডেৰেও গৈ কানেক্ট হ'ব, এইটো সাইডেৰে গৈ কানেক্ট হ'ব. যদি তেনেকুৱা হয়, তেতিয়া আমি ডায়মণ্ড ষ্ট্ৰাকচাৰটোৱে পাব পাৰিম, কিন্তু কাৰ্বনৰ জেগাত এনেকুৱাকে লংগাৰ এটা লিংকাৰ আমি তাতে ক্ৰিয়েট কৰিব পাৰিম. So that was the first origin of the idea about this metal organic framework. So তেখেতে তাৰ পিছত তেখেতে এই আইডিয়াটো লৈ আগবাঢ়িলে. আগবাঢ়াৰ পিছত when he has first synthesized, this is the compound that they have synthesized. I have just shown you, মই আপোনালোকক এই জাস্ট এৰিয়াটো আপোনালোকক দেখুৱাইছিলো. এই কাৰ্বনটোৰ লগত আপোনাৰ এই বেনজিন ৰিং প্লাস দিস সায়ানো গ্ৰুপ was present. So this carbon
share কৰিব নেকি? স্ক্ৰীন টু share কৰিব লাগিব আকৌ.
স্ক্ৰীন টু কৈছিলো মই জাস্ট
আপনি আনশেয়ার করলেন।
So now is it visible?
Yes.
Okay. So then what he has done, he has actually gone and created this compound. In this compound, he has used this tetrahedral linker. In this linker, if you see exactly like I have shown you just now in the model, I have shown you this part. So this part now can connect to a copper ion instead of a carbon. So what he has done, he has taken this copper ion, and this copper ion with this tetrahedral linker, he has just created a diamond-like structure. So that was the first structure in 1989. So he started teaching from 1974, and finally he has arrived at his idea 15 years later with this compound published in 1989. So that publication paper, if we look, this is the structure that he has created with this ligand, and in this structure he has these cavities. These cavities are filled with solvents, which is nitrobenzene, and a counter anion, which is BF4-. So আমি এনেকুৱাকে ভাবিব পাৰো যে এইটো এটা ডায়মণ্ডৰ নিচিনা, এই কাৰ্বন কাৰ্বন লাগি থকা ষ্ট্ৰাকচাৰৰ নিচিনাই, কিন্তু সেই বণ্ডডাল এতিয়া ইলংগেট হৈ এনেকুৱা এটা পুৰা ষ্ট্ৰাকচাৰৰ ক্ৰিয়েট কৰিলে, আৰু পুৰা ষ্ট্ৰাকচাৰৰ ভিতৰত বিভিন্ন ধৰণৰ সলভেন্ট আৰু আয়ন মলিকিউল আছিলে। সো structure বিষয়ে এইখিনি ইয়াতে বিশেষকে দিয়া আছে, that he has created a very open diamond like connectivity. This network occupies less than half the volume. So the network occupies half the volume, the other half is occupied by the solvent molecule trapped inside the pores of this particular molecule. The large intraframework space being filled by highly disordered solvent molecules together, and whole molecule is undoubtedly crystalline. ইয়াৰ আগতেও পলিমাৰ কেমিষ্ট্ৰি আছিলে। পলিমাৰ কেমিষ্ট্ৰিত আমি জানো যে এটা অৰ্গেনিক মনোমাৰ লৈ আমি এটা পলিমাৰ ক্ৰিয়েট কৰিব পাৰো, কিন্তু অৰ্গেনিক পলিমাৰৰ ক্ষেত্ৰত সেই গোটেই কম্পাউণ্ডবোৰ এমৰফাছ হয়। They are not crystalline. That means they have not have repetitive unit in a precise position. Precise structural information is not known for the polymers. So head to a milestone with this compound, and this is the first compound that sets the area of metal organic framework. At that time, this was the most unusual material. In 1989, this one was the most unusual material at that point of time. Okay. So next, Robson, so he has given one more idea, that instead of that, just now I have shown you this ball and stick. So we can use these organic compounds as the rod or the linker, and the metal ion as the node. So we can connect this node by this linker, and then we can create a structure. So তেখেতে কি কৰিলে, তেখেতে এই এটা স্কোয়ার গ্রিড কম্পাউন্ড রিপোর্ট কৰিলে নেক্সট ইয়ার ইন 1990, য'ত তেখেতে মেটেল আয়নক 4 ডেজ বাইপিৰিডিন, য'ত নেকি আপোনাৰ নাইট্ৰোজেন ডোনৰ এটম আছিলে, জাস্ট কানেক্ট কৰি এনেকুৱাকে এটা স্কোয়ার গ্রিড কম্পাউন্ড ক্ৰিয়েট কৰি এই rod and node, like linker and node conceptor তেখেতে আৰম্ভণি কৰিলে। So this was the first contribution of Professor Robson. Next come to picture is the German scientist Susumu Kitagawa. So what Susumu Kitagawa has done, so he has a beautiful philosophy for his work. He said to create usefulness of useless, to create something useful from a useless. There is a story behind that. What is the story behind that? So he have developed this kind of two-dimensional compound, developed one of the first porous molecular structure, and when he created these compounds, initially the community did not took them seriously. People used to say them, okay, you guys have created some new compounds, they looks good, but what are the use? These compounds are useless. So because of that, actually Professor Susumu Kitagawa faced many rejection. And because of that, his many projects were initially rejected because people cited that these compounds are useless, they do not have much use with the compound. But as many other scientists, they kept working on their ideas, and eventually they have shown why these compounds are so important. So next, in next few years, what he has shown that he can actually develop some of these compounds. For example, here, this compound is known as tongue and groove compound, in which it has a tongue from one part of the framework that exactly fits into the groups of the other compound. So this is more like the one that we read about enzyme lock and key mechanism. So similar to that. So it actually fits into the group of the other structures, and it creates some channel within the structure. So in that channel, so what Susumu Kitagawa was able to show that you can actually, so up until now, whatever compound you have synthesized, they have the pores, but these pores are filled with solvent. When you try to remove the solvent, the structure used to collapse. So this one was one of the first examples where he could show that you can actually put in methane molecule or small gas molecule, and then you can take out this molecule from the structure without disturbing the compound. So this one was very big breakthrough. So now what he showed that you can actually create a flexible MOF in which you have this framework structure. In the framework structure, what you can do, you can put in this small gas molecule like hydrogen, carbon dioxide, methane, and you can take out this gas molecule from the structure, and then you can put in as well. So this one was a huge contribution, and that showed the usefulness of this compound. Why these compounds? First use of this compound, that even if you remove the solvent molecule, the compound are stable, and you can reabsorb the solvent gas molecule, and you can create them as a space in which you can put all these different small gas molecules. Okay, so that was the contribution of Kitagawa. So we have seen Robson has started the area with the idea. Kitagawa showed that, okay, these are not that useless. You can use them for various kind of application. Next came Professor Yaghi, who is probably the most well-known out of the three. So he also had a very challenging childhood. He was born in Jordan, I think, to a Palestinian parents who took refuge in Jordan, and he has a very difficult childhood. What changed his mind was that he went to a library in Amman, and he was very inspired by the structural chemistry by Linus Pauling, and he realized that the way out of that difficult scenario is education. So he took it very seriously, and then he ended up in US, and he did his PhD, and then he has actually extended this whole idea of metal organic framework to a very high level, that you can precisely now make this molecule according to your design, and you can also create ultra high porous compounds. So what Yaghi did, so he has started with some of these zinc clusters, And he is the one who has introduced. So previous to this, people were using like 4,4-days bipyridines, which are not charged molecule, they are neutral molecule. But he is the one who has first introduced benzene carboxylic acid. So the carboxylic group of the benzene will go and bind with the metal, and then it will eventually form this kind of three-dimensional structure. And he has given that term. So until now, Robson did not name any of his compound as metal organic framework. Kitagawa started to use the word porous organic polymer, porous coordination polymer. Yaghi has started the name metal organic framework, and from there it has started to popularize the area. And then he created in 1999 MOF5, one of the most well-known and highest cited and most widely used metal organic framework, made out of zinc and benzene dicarboxylic acid to form this kind of a framework structure. So what Yaghi showed, that not only the like benzene carboxylic acid, dicarboxylic acid, you can have different kinds of functionality, but still you can have the same structure. That means he said that these are like modular building blocks, like Legos. You can just connect them with the connector and you can create the framework structure. So what he has shown, that you can go from this, you can introduce different functionality. Not only that, you can also increase the size of the linker from this to little bit, then we biphenyl, then to triphenylic system. You can keep on increasing. So what it will do, it will keep on increasing the space that is in between the framework structure. So you can control the porosity of the molecule, or you can tune the porosity of the molecule. So these compounds were known as reticular chemistry or isoreticular chemistry. This process is also known as reticular or isoreticular process. Next, মই কেইটামান এক্সাম্পল দিব বিচাৰিম কেইটামান ৱেল নোন মফ কম্পাউণ্ডৰ বিষয়ে তাৰ পিছত আমি আৰু অকমান ডিটেইলছত যাম গৈ পেলাই আমি এপ্লিকেশন কেইটামান চাম সো এই প্ৰথম কম্পাউণ্ডটো হল MOF 303 MOF 303 is very important মই আপোনাক দেখুৱাম পিছত যে MOF 303 এ এটমস্ফিয়াৰৰ পৰা ওয়াটাৰ ক্যাপচাৰ কৰিব পাৰে MIL 101 MOF is metal organic framework. MIL মানে হল materials of Institute of Lavoisier. So yeah, Franceৰ পৰা অহা Professor Gerard Federer গ্ৰুপৰ পৰা অহা compounds. So MIL compound can be used for hydrogen or carbon dioxide absorption. Next, UiO 67. UiO 67 stands for University of Oslo, Norway. University of Oslo. University of Oslo UiO 67 is a very well-known MOF that can be used for absorbing perfluoro compounds from water for water treatment. Three other examples: Z8. Z8 stands for zeolite imidazole framework. Ihotor structure zeolite or logot samanjanya ase. They are quite similar to the zeolites. They can be used for mining rare earth elements. Then we have Calgary framework material 20. So these are used for absorption of carbon dioxide in the cement factories. Then we have Northwestern series of compounds, Northwestern 1501. So these are very large surface area materials, so they can absorb hydrogen at room temperature to a great extent. So these are some of the well-known MOF, and this information that I have shown you up until now is directly connected from the advanced information from the Nobel Prize website. So next, just to give you a little idea about the MOF, as I have told you. So these MOF structures can be of different dimension. They can be one dimension. They can be a two-dimensional layer-like structure, or they can be a three-dimensional structure. This structure can have various topologies like this. They can be hexagonal honeycomb-like structures. They can be like these square structures, or they can have these, kind of, buckyball kind of structures as well. So when we talk about the ligand, why these compounds are very important is because you can change the ligand. So you can now have n number of ligands of different type. For example, bipyridine, this tetrahedral units, dicarboxylic acid, this whole range of carboxylic acid, bipyridines, as well as imidazole, nitrogen donating ligand, everything we can have. So we can change it. So you have a permutation combination of enormous number. So you can create enormous number of compound out of these ligands. So why these compounds are very important, as I told you, because they have very good surface area, and here actually because of their crystalline nature, these pores remain intact. So that means we can go and access each and every atom inside the surface of that structure. So that gives rise to something, very high surface area material. How big are these surface area? So for example, MOF5 has a surface area of 4,400 meters square per gram. How much is that? I will just tell you in the next slide or so. And then one of the highest one you can see is that DUT. This is 7,800 meters square per gram. So this is like, if we have the compound, if 100% porosity is there, then you can go to 10,000. That means for this per gram of molecule, almost 80% of the structure is vacant. Only 20% is the framework, and rest of the 80% is the surface that you can use for various applications. So now, this is an image from the Northwestern University's football stadium. So in one of the publications where they have put the analogy that if you have this 1 gram of this NU 1501 MOF, that surface area is actually 1.3 times the surface area of this football arena. How is that possible? That is possible because the compound has very small microporous, or nanoporous, less than nanometer size, pores or channels of precise structures there. So now if you think in a 1 mm crystal, how many more of those channels that you can have? So because of that, you have this enormous surface area in a very small 1 gram of that compound can have this much surface area. So this is one of the most important application of or properties of this material. So this is the timeline as I have shown you. So around 1990, it is there. These compounds are there. Some of these compounds are there in 1950, like the Prussian blue and the other compound. But it has started from 1990 or so. And then these all very important compounds has been developed. And now you have this compound with surface area that is now going up to 8,000 meters square per gram. So now this area of MOF in the last 20 years or so has given many other areas. Now people are hearing a lot more about POF. POF is nothing but covalent organic framework. Like the metal organic framework, now you don't have the metal ion, you only have the organic linker that will connect and it will give you a crystalline organic polymer. So they are different from the normal polymer in a way that they are crystalline in nature. So now you have metal organic framework, zeolite imidazole framework. These are all subclass of metal organic framework. Covalent organic framework, porous organic polymers, hydrogen bonded organic framework, or polyaromatic framework. So these all are various class of materials that has been, born out of metal organic framework compounds. If we talk about their synthesis, there are different types of synthesis that are involved. So for example, we can do them in a normal solvent thermal synthesis. Solvent thermal synthesis means there will be solvent, and then we can use temperature as well as pressure there to create the crystal. So it is very similar to our nature, Mother Nature, in which in between under the earth crust we have all these zeolite minerals that are formed out of the pressure and the temperature, geochemical pressure and temperature. The similar kind of method gives rise to this MOF as well. Then we can have these different other methods, like we can use microwave as the energy source. We can use now sonochemical synthesis. We can have electrochemical synthesis. Various syntheses are there that can be used for this MOF synthesis. About the properties, as I say, the main properties arise from the surface area, that is the space it will give. There will be properties from the metal ion. If we want to talk about magnetic properties or luminescent properties, that can come out of the metal ion. And the linker can give you different kind of catalytic properties. So these are various kind of properties that these range of molecules can give you. And in terms of application, I will discuss two applications, but there are many applications. For example, they are used as sensing material. They can be used as antibacterial material, drug delivery, various kinds of catalysis, gas storage, energy storage material, as well as electrocatalyst, and many others. Okay, so the gas storage that we talk about is very important in this molecule because of the enormous surface area they have. So there you can have all these small acetylene molecule as well as carbon dioxide. You can store methane. Toxic gas separation we can talk about. Also we can talk about hydrogen storage. So one example I will tell you, that is the water absorption, which actually lead to the many believe this is one of the application that resulted in the Nobel Prize award. This area was there from last almost now 40 years, but this has pushed the Nobel Committee to take this very seriously about this water absorption. And why is important, I will just go through in this next few slides. So this is a structure, MOF structure, made up of aluminium and pyrazine dicarboxylic acid. Pyrazine dicarboxylic acid means these are all carbon, these are carboxylic acid, and here you have two nitrogens. So it gives you this beautiful, square grid kind of compound. Now, when we take this compound and if we add water, it can actually hold lot of water in this space that are there in this particular structure. So this is one of the compound of this, MOF 303 compound. If you look at the water absorption capacity, you see over here. So this is the water absorption graph. If we put the water and if we increase the pressure a little bit, then you can see it absorbs in this direction. And when we release the pressure, so you can see it actually release the water molecule very well in a very low pressure. And if you look at the H2O uptake, so for each molecule of the compound, like one aluminum hydroxide compound with an aluminum dimer can take up almost 10 water molecule, which is huge. So now, similar to other compound I will show you. One is MOF 801, in which you have this kind of a carboxylic acid with zirconium cluster to give you this three-dimensional compound, and another one in which you have this zirconium cluster and this tetrahedral carboxylic acid group to give you this three-dimensional structure. So these three structure, MOF 841, 801, and 303. These three, if you look at them, you see all of them shows very good water absorption. MOF 841 is the highest, okay, with a very good release, almost 100% release at low pressure. So that actually give us the idea, or give the scientists the idea that this can be actually used for absorption of water in various condition. For example, if you look at the area, it started in June around 2016, where water absorption or production of this kind of material was only 0.01 liter per kg of MOF per day. That has now increased to, if you look at here, so now if you use one of these material, you can actually have 100 liter of water per kg of MOF per day. So you can actually get 100 liter of water from 1 kg of MOF. That is actually enormous in areas where people are lacking of drinking water. So you can look at this MOF 303 that was planted in various cities across the world. If you look at here, we have Chennai, Dhaka, Delhi, London, LA, New York, as well as few desert areas, Mojave Desert and some other deserts. So if you see over there, you can see, depending on the relative humidity, you can absorb the water. So in areas like, for example, if we see one of these Chennai, which is very humid, you can see you can have almost 80 liter of water per day, almost 80 to 100 liter of water per day. If you look at Delhi, in the summer or in that period, there are less, almost around 40 liter per kg. But if you are in the monsoon times, then you can see it can almost reach around 90 and then it comes back. In desert areas, if you look at these yellow ones, they are low, but still if you look at that, they are still, you can get 20 liter of water per day for each kg of water. So that actually changed the area. And now if you look at, this is an image of Professor Yaghi. So he was in one of the desert, if I have that, I think yeah, it is in Death Valley. So in the Death Valley, what he has done, he has actually shown that you can have this device made out of MOF. So this inside cartridge is connected with MOF, and then there are some hydrophobic coating so that water can be trickled down. So you can use a tap there, and you can actually have drinking water directly from air. So basically, you are opening a tap in the air, and you are filling your glass, and you are drinking them. So that can be of, huge potential. Why? Because according to US Geological Survey, that estimates that around 13,000 cubic kilometer of water is present in the atmosphere, which is around 14% of what is found in all the lakes that are present in the world. So that is huge, and it can, boost up the areas where, there are no, safe or pure drinking water. So now lots of startups are there which are trying to make these devices. So there is this company called Etoco, which was founded by Professor Yaghi, which is making this, installable devices from which you can pluck water out of thin air. So this is the closed lookup of the device from which you can actually collect the water. So that is one use. The next one use I will discuss, that is about the fuel car. So probably most of you have heard about hydrogen run cars. So the hydrogen run cars are considered to be very unique, because in which you will burn the hydrogen with oxygen and you will emit only water. So that's very good for our environment. However, one of the problems that is associated is that when we are putting hydrogen, we have to put the hydrogen at a very high pressure. Otherwise, we will, because it's a gas, so we cannot store mass gas and we cannot run it for longer distance. So because of that, you have to pressurize that. So when we use that high pressure for hydrogen, so hydrogen is very difficult gas to handle, because whenever there is a spark, it can actually catch fire. So higher the pressure, higher the risks that is involved with this kind of application. So what one can use is that one can use one of these MOF compounds. For example, this is dihydroxy isothalic acid. When we use this one, that can actually reduce the pressure that needs to keep a particular amount of gas. Why is that? Because now this gas molecule or the hydrogen molecule can interact with the internal surface of the MOF, and they can stick to this one in a for energy to stick to the surface. So because of that, in the same pressure, what we can do, we can have more hydrogen that is present in the car. So are there any examples for that? For example, if you look at here, Toyota and Hyundai started some of these. For example, Toyota Mirai and Hyundai Nexo, these were hydrogen fuel cell. They do not use MOF. They are hydrogen fuel cell cars. But overall, this has been, pushed back because of the now the lithium ion based car. So because of the lithium ion based car, this did not took off that well. However, there was this example of this car, that one was done by BASF company, where they have used MOF, and because of the use of MOF, what they could do, if we don't use the MOF, let's say you can travel with a full tank of methane 200 miles or 200 kilometers. If we use the MOF, then you can actually have 3 times higher fuel compared to the tank that do not use MOF. So that means now you can extend your range from 200 to 600. So this one was demonstrated by this, Eurofuel Asia 2 in 2007 from Berlin to Bangkok using methane as the gas. So they did not use hydrogen, they used methane. So with that, actually now people are trying to use this, hydrogen fuel bus. So in India also now there are a lot of hydrogen green fuel initiatives are going on. So recently last year, I think in Ladakh, 5 buses were introduced in which they use hydrogen. Here they do not use MOF, they use hydrogen only. But why I have shown you this one is because recently what we have seen in London, that people are using this, cryogenic MOF hydrogen tank. So when we use this MOF hydrogen tank, so either what we can do, if we use the same pressure, that means we can increase the distance that can be covered with the tank, or we can reduce the pressure at least by 3 times without using of MOF. So if we use the MOF, the pressure can come from 300 bar to 100 bar. So now less pressurized means much safer it is. So there are a lot of initiatives going on in this direction to use it, for this kind of application, apart from many other applications that are present there. In terms of commercialization, there has been a large number of companies and large numbers of trials are going on. There are lots of MOFs that are being used as drug delivery agent. There are lots of energy related applications are there. Some of the MOFs are also used as drugs. So various things are there. So there are companies who are now selling these MOFs. They are available. We can buy it. For example, BASF has these big large scale productions that are there. We can buy various things from them, as well as Sigma Aldrichs. And if we look at the area, if you see the area, so this is the growth of the area. Around 1990, it has started. And until now, you can see almost like 120, 130,000 MOF has been discovered. And possibility is enormous with the already synthesized MOFs. There are a lot of applications are there. We can do a lot of post-synthetic modification, many other scenarios that can be achieved through these MOFs. And just to conclude, these are some of the books that if anyone is interested to know about this, so these books can be read. And then finally, thank you all. আপোনালোকৰ মনোযোগৰ বাবে ধন্যবাদ for last 40-45 minutes or so. And this is our group in which we are working in IIT Patna. And these are some of the images of IIT Patna, Bharatiya Prajuktibidya Pratishthan Patna. So if you guys are around, যদি আপোনালোক কোনোবা পাটনাত কেতিয়াবা কিবা কাৰণত আহে, so I'd be happy to host you at IIT Patna. So thank you all for your attention.
Thank you, Debajit Da, for this wonderful lecture. Apuni MOF গোটেই ফিল্ডটো আমাক একদম ষ্টাৰ্টিং অৰিজিনৰ পৰা আৰু আজিৰ প্ৰেজেণ্ট ষ্টেটাছলৈকে আৰু প্লাছ কাৰেণ্ট এপ্লিকেশ্যনছবিলাক ৰিয়েল ৱৰ্ল্ড এপ্লিকেশ্যনবিলাক আমাক সুন্দৰকৈ বুজাই দিলে। আমি ভাবিছোঁ আমাৰ সকলো 15 মিনিট শিক্ষাৰ সকলোখিনি ষ্টুডেণ্ট আৰু প্ৰেজেণ্ট আজি উপস্থিত থকা সকলোখিনি মানুহ যাতে এই সুন্দৰ লেকচাৰটোৰ পৰা উপকৃত হৈছে। I want to open this floor for any questions from our own members as well as the students. You can raise hands and also type in the chat box that we have. If anybody has any questions, please.
আমাৰ মাজত জুৰিটি আছে, জুৰিটি তোমাৰ কিবা প্ৰশ্ন আছে নেকি? তুমি আনমিউট কৰি সুধিব পাৰা।
প্ৰথমতে দেৱজিৎ দা বহুত ধুনীয়া প্ৰেজেণ্টেশ্যন, স্পেচিয়েলি আপুনি শ্লাইডত বহুত মানে ইট ৱাজ এ ভেৰি ৱণ্ডাৰফুল প্ৰেজেণ্টেশ্যন। শ্লাইডবোৰো বহুত ভাল হৈছে আৰু অভাৰঅল মানে একদম ডিস্কভাৰীৰ পৰা আৰম্ভ কৰি এপ্লিকেশ্যনলৈ ইট ৱাজ এ ভেৰি নাইচ প্ৰেজেণ্টেশ্যন। মোৰ কেইটামান বেছিক কুৱেশ্যন আছে। প্ৰথমতে প্ৰফেচাৰ কিটাগাৱাৰ ফ্ৰেমৱৰ্ক ডিজাইনৰ ওপৰত। The question is how easy is to dissolve the gas after adsorption, because it depends on the pressure also. And apuni dote water adsorption or khetrot aru prothomote jete basic idea to disile tetia apuni heri adsorption plot eta dekhaisile pressure or logote, and which shows the adsorption desorption pathways are very similar. More question to hoise jetia adsorption hoar bisot desorption hoar agot সদায় হেতু ইজিয়ে হয় নে কেতিয়াবা গ্যাস মলিকুলস তাত ট্র্যাপড হ'ব পাৰে, so that if can we see some hysteresis in the adsorption desorption path? That is one of the question. And tarpisor next question to is related to water adsorption, the applications in the water adsorption process. And question to is is there any challenges in the real application, and how effective the process in low humidity condition?
Thank you, Juriti. তুমি গোটেই মানে ভাল কুৱেশ্যন কৰিছা। এই গোটেই প্ৰব্লেম এখিনি তেওঁলোকে সকলোৱে ফেচ কৰিছিলে। চ' প্ৰথম যদি আমি মই প্ৰথমতে তোমাৰ হেৰিলৈ আহোঁ, তুমি এডজৰ্পশ্যনৰ বিষয়ে সুধিছিলা। চ' এডজৰ্পশ্যনত প্ৰথম যেতিয়া আমি এডজৰ্পশ্যন ডিজৰ্পশ্যনৰ কথা কওঁ, প্ৰথম প্ৰায় 5 বছৰ মানে অলমষ্ট 90ৰ পৰা 96, 97লৈকে যেতিয়া মলিকুলবোৰ তোমাৰ কম্পাউণ্ডবোৰৰ ভিতৰত যেতিয়া তোমাৰ ৱাটাৰ মলিকুল বা সলভেন্ট মলিকুলবোৰ থাকে, সিহঁতৰ এটা ইণ্টাৰেকশ্যন থাকে ছাৰ্ফেচৰ লগত। যেতিয়া আমি ডিজৰ্পশ্যন কৰিবলৈ যাওঁ, যেতিয়া সলভেন্ট মলিকুলটো ওলাই যায়, তেতিয়া কি হয়, ছাৰ্ফেচটোক একেলগে টানি আনাৰ কাৰণে কোলাপছ হয়, গোটেই ষ্ট্ৰাকচাৰবোৰ কোলাপছ হয়। প্ৰথমৰ দিনা গোটেইবোৰ ষ্ট্ৰাকচাৰবোৰ কোলাপছ হোৱা আৰম্ভ হয়। লাহে depending on design, choice of the metal and choice of the organic linker, and then tuning the interaction between the gas molecule or the solvent molecule with the surface, lahe manue compound pabole arambho korile jibilakot structure would still stable because of the very strong bond, they are still stable. So tumi water molecule tapra ulabo para and then tumi humabo para tate eta notun conceptoru udbhavan hol, that is called breathing molecule. Like when we breathe, our lungs expand and then collapse. So if the structure is dynamic enough, then when the gas molecule comes, they can actually expand, and when it goes out, they can collapse. So all these things actually will appear in the plot that I have shown. I have shown you a very simple plot. There are many other that will have adsorption will happen, desorption will never happen.
Never. Yes.
There will be someone where adsorption will happen, desorption will happen with a delayed desorption with a hysteresis loop. So many examples are there. So this one was the first question. And then second question you ask about, I think, the water absorption.
Water absorption, yes.
Yes, water absorption was also there are issues. For example, the absorption is very good when the relative humidity is high. At low relative humidity, it is difficult. But there are molecules like the aluminum compounds and all, they are already known to be hygroscopic enough. So there you can have this, water. Obviously, if the humidity is low, the absorption will be. Also, again, there also, I have shown you few compounds. These are the compounds out of, probably thousands of compounds people have tried. Many of them will not absorb water as soon. Most of the MOFs has a very has a property that they are not stable in water. So most of them will get dissolved. So that is also one thing we have to think about. We have to use the MOF which are only stable for water. And also that absorption desorption. So these are some areas I think people will still like to work. But if you can see in last 10 years, there has been a tremendous improvement, almost 100 times higher now we are. And also, not only because of the material, but also because of the development of many hydrophobic molecules that we will be used as a coating into that one, so that once the water is absorbed with the hydrophobic molecule, it will trickle down and it will settle in the bottom. So design of the cartridge and everything takes, into account, and it's improving. There are a lot of challenges are also there, but yeah.
Yeah. And the last question is for the hydrogen gas absorption part for uses of energy applications. So there would be like we have to use the extreme conditions. And for the scalability, industrial application or in the large scale applications, so there would be some cost issues because it needs extreme conditions. So what do you think about that challenges?
See, already, as I have told, that people are thinking about using hydrogen in public transport. Like China has already, I think, developed a car engine, train engine that can run on hydrogen. India is also working on that. Many other countries are working. So people knows that these are extreme, but with the safety you can use it. For example, as I have shown you that in India also people are now started using this hydrogen run bus, because we already use methane, CH4, like the CNG we use in India. People are also thinking about hydrogen, even though methane and hydrogen are not same, because methane it will not burn as explosively as hydrogen. So you have to be careful in that. So it is already there. But if people introduce MOF, then as I have told you, because MOF will give the surface for the hydrogen to absorb. So then what you can do, you can reduce the pressure that will be needing to absorb the same amount of hydrogen. For example, without the MOF, if we can go, let's say 300 bar pressure, with the MOF, we can bring down the pressure to 100 bar. And why is that happening? Because the sites will have some preferential absorption for the hydrogen and surface area is very high. So that can actually help. So I can see certain application of this in this kind of ones. But public, like the personal transport, like the car that I have shown, people are almost stop producing the hydrogen fuel cell car. That is because of the popularity of the lithium ion car. So I think if there is a scarcity in lithium, then people will look into hydrogen run car. But for public transport, people will still look for hydrogen run buses and others.
So you mean the cost cutting might come from the low pressure thing?
Safety, I would say safety. Cost, I think eventually it will be taken care of. When we do it in lab, the cost is very high. But with the pilot project and other, for example, BASF has already shown that you can actually have, tons of MOF can be synthesized, even though the properties may not be same for a, let's say, if you create something in lab, if the surface area is, let's say, 8,000 meters square per gram, in that large scale synthesis, it may be only 2,000 per square per gram. But I think if you cut down the cost, that will also, be helpful. Okay. Property may not be exactly same, but the money that you will be spending and the kind of use that you will be having, for that it may be sufficient.
Sufficient. Okay. Thank you so much.
Thank you, Duriti.
So, Debajit, I had a question.
Yes,
this is more generic, more not technical. Basically, I want to know in every Nobel Prize, there will be some people whose contribution won't be recognized. I mean,
Yes,
there may be many other scientists who are working in this COF MOF area and whose
yes.
contribution may have been overlooked or like could not make it to the top three of this panel. Can you name some of those scientists and who are
So,
working in these areas?
yes, so good question again. So when the first time the MOF Nobel Prize, so basically we were expecting from last 10 years that Nobel Prize will be given to the area of MOF. So whenever we used to have your, chai time discussion, we used to say that 3% will get the Nobel Prize. That will be Susumu Kitagawa, Omar Yaghi, and we thought it will be Gerard Ferre. Gerard Ferre is a very he's a scientist in he was a scientist in Paris, France, from where that name MIL, Material Institute of Lavoisier, that was there. Unfortunately, he died few years back, and also probably we are not that wise enough because we didn't. Nobody used to talk about Robson. Robson gave the idea, and he's not very active. He's very active in terms of teaching and other, but in terms of the area, he's not that active like Kitagawa and Yaghi. So we thought that it will be Gerard Ferre. So these three, and I think Robson was there, Gerard Ferre because he died. So probably these three were given. One more person was there, Japanese scientist. His name is Makoto Fujita. So he was more into the application part of it. So we always thought he may be there, may not be there. He's an outlier. That that they always used to do some of this prediction that who will get the Nobel Prize. So there, apart from Omar Yaghi, there is a professor who was there in our Northwestern only, my department only, Omar Farha. So he has popularized the area in terms of the application, all these NU 1000, NU 1500. So a lot of people thought that he might be also there, even though he started very late, but he had real contribution in the later, you can say last 10 to 15 years in the MOF area. So these three names I can think of. There are many others, but probably one that has missed was, I think, Professor Gerard Ferre. And this is something that in Nobel Prize, that they do not give it, they give it only to the living people. So I think, and COF is a very new area, so that will have different area. So this is a kind of come out of MOF, so that will have future and future things. So not yet.
Yes, so every time I remember, and there is a poll before the Nobel Prize, sometime in May, June se start hota hai, and October Nobel Prize are awarded. And Omar Yaghi is always there in last 5 years almost, I remember.
Yes, yes.
But every other time they choose different areas, sometime medicinal chemistry, sometime material chemistry, but this time.
So we are happy that it is from last few years. They are giving it to chemistry actually. That's
Chemistry,
good.
yeah.
Because
No,
previously chemistry and I think physiology and medicine, I think. So most of
physiology
the
or
thing,
medicine, yes.
yeah. So most of the time it goes to people who are working on mostly biological system, which are very important and relevant. But we thought that it was a little bit overlooked, the chemistry. But last few years it has been given to chemistry people.
Yes. Thank you. Rifadda and Hironada, any other questions?
বহুত ধন্যবাদ Debajit for such a nice lecture on this complex topic. মইতো বাৰু chemistry student নহয়, but তথাপি তুমি ইমান সুন্দৰকৈ বুজাই দিলা আৰু তুমি মডেলো দেখাইছা. It's really inspiring for all of us, and আশা কৰোঁ ষ্টুডেণ্ট সকল তোমাৰ লেকচাৰৰ পৰা বহুতখিনি উপকৃত হৈছে. মই প্ৰশ্ন দেখা নাই এতিয়াও. হিৰণ্যদা, আপোনাৰ কিবা ক'ব লগা আছে নেকি?
নাই, মই দুটা কমেণ্ট ফেচবুকত দেখিছোঁ, এটা কমেণ্ট আৰু এটা প্ৰশ্ন. কমেণ্টটো হৈছে চিৰঞ্জীৱ গগৈ, তেওঁ পোলেণ্ডত থাকে বোধহয়. তেওঁ লিখিছে, থেংক ইউ ছ' মাছ দেৱজিৎ দা. As a MOF chemist, I must say that those who attended the lecture from other backgrounds were also able to understand our research topic easily. So সেইটো চিৰঞ্জীৱ গগৈ পোলেণ্ডত তেওঁ ৰিচাৰ্চ এছিষ্টেণ্ট প্ৰফেচাৰ ইউনিভাৰ্চিটি অফ ৰকলো, if I pronounce it correctly. সেইটো আৰু এটা প্ৰশ্ন এটা আছে ৰঞ্জন সন্দিকৈ তেওঁৰ how high hydrocarbon density in fuel station impact in real speed and mileage of vehicles. I want the answer from the insight of metallic chemistry.
Okay. তো প্ৰথমতে চিৰঞ্জিত ধন্যবাদ ৰঞ্জনৰ কোৱেশ্চনটো আকৌ এবাৰ কৈ দিব নেকি হিৰণ্যদা
তেওঁ লিখিছে how high hydrocarbon density in fuel station impact in real speed and mileage of vehicles. I want the answer from the insight of metallic chemistry.
ৰঞ্জন মই তোমাৰ কুৱেশ্যনটো প্ৰথম পাৰ্টটো মই উত্তৰ দিব নোৱাৰিম কাৰণ মই খুব বেছি মোৰ আইডিয়া নাই আচলতে কেনেকে মাইলেজ বা কাৰ মাইলেজৰ ওপৰত কেনেকে কাম কৰে যদিও মই দেখাইছো যে কেনেকুৱাকে আমি হাইড্ৰোজেন গেছ ইউজ কৰিব পাৰো এজ এ ফুয়েল মোৰ ইন টাৰ্মছ অফ দ্যাট তোমাৰ কুৱেশ্যনটো মই নাজানো যদি মফৰ ৰিলেটেড তুমি কিবা বুজাব বিচাৰিছা মই বুজি পোৱা নাই বাট ইন টাৰ্মছ অফ মাইলেজ মোৰ তেনেকুৱা আইডিয়া নাই তুমি হোপফুলি মোৰ ইয়াতে তুমি ইমেইল আইডিও আছে তুমি যদি মোক যদি মই বুজি পোৱাত অসুবিধা হৈছে তোমাৰ কুৱেশ্যনটো যদি পঠিয়াই দিয়া মেবি উই কেন ডিছকাছ ফাৰ্দাৰ
তোমাৰ ইমেইলটো কোৱাচোন দেৱজিত মই ফেচবুকত টেক্সট কৰি দিব পাৰোঁ
মোৰ ইমেইলটো হ'ল দেৱজিত মোৰ নামটোৱে DEBAJIT@iitp.ac.in
thank you হিৰণ্যদা আৰু কিবা দেখিছে নেকি
নাই আৰু মই কুৱেশ্যন বা তেনেকৈ কমেণ্ট দেখা নাই মোৰ ফালৰ পৰা থেংক ইউ দেৱজিত খুব সুন্দৰ মই বিজ্ঞানৰ ছাত্ৰ নহয় কিন্তু তোমাৰ যিটো আজি প্ৰেজেণ্টেশ্যনটো আলোচনাটো খুবেই সুন্দৰ হৈছে খুব ভাল লাগিল মোৰ এটা কথাই মন চুই গ'ল যে ৰবছনে তেওঁ পঢ়াই থাকোঁতে আমি কেতিয়াবা টিচিং ৰিচাৰ্চ এইবিলাক লৈ পেলাই অলপ কথা পাতোঁ কেনেকৈ ইটোৱে সিটোক ফিড ইন কৰে গতিকে তেওঁ পঢ়াই থাকোঁতে কেনেকৈ তেওঁৰ মনলৈ এটা ভাৱ এটা আহিলে আইডিয়া এটা আহিলে ধাৰণা এটা আহিলে সেই কথাটো সেই মানে কাহিনীটো শুনি তোমাৰ মুখেৰে ভাল লাগিল সেইটো যে আমাক টিচিঙে আমাক ইনফৰ্ম কৰে কেতিয়াবা আমাক কেতিয়াবা আইডিয়া দিয়ে দ্বিতীয় কথাটো কিটাগাৱাৰ কথা কওঁতে তুমি বহুত ৰিজেকশ্যনৰ কথা কৈছা বোধহয় সেই কথাটো খুব গুৰুত্বপূৰ্ণ ৰিচাৰ্চাৰ যিবিলাক গৱেষক আছে তেওঁলোক কেতিয়াও নতুন আইডিয়া লৈ এটা বহু সময়ত তেওঁ নিৰাশাত ভুগিব লগা হয় যে ৰিজেকশ্যন হয় কিন্তু সেইটোত যে এৰি দিব নালাগে সেই কথাটো সোমাই আছে এটা কথা বুজিলোঁ যে যিটো মফৰ ধাৰণাটো তুমি বুজাই দিলা তাৰ পৰা আমাৰ বহু ধৰণৰ ব্যৱহাৰিক জীৱনত লাভ হ'ব পাৰে খোৱা পানীৰ পৰা আৰম্ভ কৰি বিভিন্ন কথা সামগ্ৰিকভাৱে তুমি এইটো ক'বা নেকি যে মানে আমাৰ যিটো পাৰিপাৰ্শ্বিক সমস্যা যিবিলাক হৈ আছে এনভাইৰনমেণ্টেল প্ৰব্লেম যিবিলাক হৈ আছে সেইবিলাক ছল্ভ কৰাত এই ফ্ৰেমৱৰ্কটোৱে এটা ডাঙৰ ৰোল প্লে কৰিব পাৰে জেনেৰেল কুৱেশ্যন এটা
মই নিশ্চয় ভাবোঁ কৰিব পাৰে কৰি আছে কিন্তু আমাৰ এনভাইৰনমেণ্টেল প্ৰব্লেমটোৱে বহুত ডাঙৰ প্ৰব্লেম চাগে এটা সলিউশ্যন নাথাকিব মাল্টিপল সলিউশ্যন লাগিব তাৰ ভিতৰত এটা নিশ্চয় হ'ব পাৰে যেনেকুৱাকৈ আমি দেখালোঁ যে খোৱা পানী বিশুদ্ধ খোৱা পানী কিছুমান এৰিয়াত আপুনি এটমছফিয়াৰৰ পৰা পাব পাৰে সেইটো এটা বিৰাট ডাঙৰ কথা যেনেকুৱাকৈ আপুনি ভাবক যে সমুদ্ৰত কেতিয়াবা কাৰণে আমি ভাবোঁ যে সাগৰত কিছুমান মানুহ যদি ট্ৰেপ হৈ থাকে কিছুমান দিনৰ কাৰণে কেইদিনমানৰ কাৰণে তাতে বিৰাট পানী বহুত পানী কিন্তু আপুনি খাব নোৱাৰে তাতে আপোনাৰ মইশ্চাৰো আছে এয়াৰত তথাপিও আপোনাৰ খোৱা পানী নাই কিন্তু তেনেকুৱা চিটুৱেশ্যনবোৰত এনেকুৱা কম্পাউণ্ডবোৰ বা এনেকুৱা এপাৰেটাছ থাকিলে আপুনি আচলতে তাৰ পৰা ধুনীয়াকৈ খোৱা পানী আৰামছে খাব পাৰিব তেনেকুৱা আছে প্লাছ বিভিন্ন ধৰণৰ টক্সিক গেছ ৰিমুভেলৰ ক্ষেত্ৰতো প্ৰয়োজনীয়তা আছে সম্ভাৱনীয়তা বহুত আছে তাৰে কিছুমান এতিয়া আমি এজ এ প্ৰডাক্ট দেখিব পাইছো হয়তো ভৱিষ্যতে আৰু নতুন কিছুমান প্ৰডাক্ট আমি দেখিব পাৰো বিশেষকৈ water cleaning, toxic gas removal, এনেকুৱা ধৰণৰ ইভেন মই দেখুৱা নাই কিছুমান হেৰিত আচলতে মফ ৰিলেটেড কিছুমান আজিকালি ফৰ্টিফাইড টেবল চল্টটো আজিকালি পোৱা আৰম্ভ হৈছে মানুহে আৰম্ভ কৰিছে তাতে তাৰমানে আমি আইৰণ লাগে কাৰোবাক আয়োডিন লাগে যেনেকুৱাকে আমি মাল্টিভিটামিন বিভিন্ন ধৰণৰ মাল্টিভিটামিনৰ কথা কৰো তেনেকুৱা আইৰণবোৰ দি পেলাই এটা বায়োলজিকেল লিগেণ্ড মাজত দি পেলাই আমি টেবল চল্টৰ লগতে মফ হিচাপে আমি খাদ্যৰ লগত গ্ৰহণ কৰিব পাৰো তেতিয়া চাগে আমি মেডিচিন নললেও হ'ব তেনেকুৱা ধৰণৰ বিভিন্ন এপ্লিকেশ্যন আছে এই গোটেইবোৰ কিমান দূৰ আগুৱাই চাগে সময়ে ক'ব কিন্তু নিশ্চয় এটা ৰোল প্লে কৰিব পাৰিব এই বিভিন্ন ধৰণৰ সমস্যাবোৰৰ ক্ষেত্ৰত আমাৰ দৈনন্দিন জীৱনৰ ব্যৱহাৰটো বিভিন্ন ধৰণৰ অৰিহণা থাকিব চাগে
ধন্যবাদ দেৱজিৎ ৰিফাত
নাই ধন্যবাদ আমি সামৰণি মাৰিব পাৰো এতিয়া পুনৰ দেৱজিতলৈ আন্তৰিক ধন্যবাদ আমাৰ ফালৰ পৰা আৰু আজিৰ এই বক্তৃতাত প্ৰদান কৰাৰ কাৰণে আৰু আজিৰ সভাত বা আজিৰ অনুষ্ঠানত উপস্থিত সকলোলৈকে আমাৰ আন্তৰিক ধন্যবাদ জ্ঞাপন কৰিছো আমাৰ পৰৱৰ্তী অনুষ্ঠান আমি এতিয়াই ঘোষণা কৰিব বিচৰা নাই কাৰণ অনাগত দিনবিলাকত বিহু আহি আছে অসমত নিৰ্বাচনো হ'ব গতিকে বোধ কৰোঁ আমাৰ পৰৱৰ্তী অনুষ্ঠান মে' মাহত হ'ব তেতিয়া আমি ঘোষণা কৰিব পাৰিম সকলোলৈকে পুনৰ ধন্যবাদ জনাই আমাৰ আজিৰ অনুষ্ঠান ইমানতে সমাপ্ত কৰিব গৈছো পুনৰ দেৱজিতলৈ আমাৰ আন্তৰিক ধন্যবাদ জনালো
Yes, ধন্যবাদ Debajit da. First of all, accepting the invitation, and then basically we had to postpone this session because of some other issues. So thank you for sparing the time. And one more thing, that all these are recorded. We'll have YouTube videos. We basically, after the lectures, who could not attend, we basically send to them, all the students. And we have a website where we upload these videos for students to come later and then watch these videos and learn something from it. And in recently আমি এখন কিতাপো উলিয়াইছো আমাৰ প্লেটফৰ্মৰ যোনবোৰ পাষ্ট লেকচাৰ্ছ হৈ গৈছে সো কিতাপখনৰ নাম কি আছিলে হিৰণ্যদা মেবি আই ফৰগট দ্য নেম পাখি মেলা সপোন so that was 2 years or lectures মানে some selected lectures which happened. It started in COVID time, this platform, and we had almost several lectures. So some of these lectures will be incorporated in the next book that we may plan in future. And etu Pakimela Khopon khon Pan Bazar ekhon kitab book store uliaise kun store hoy student stores hai. So it is available online and other stores. So bhovishyote any chemistry related lecture dibole apunak amantron korim apunar research related ajitu nohol but you can also we also do some kind of research related other than this general topics also. Thank you so much from my side and entire 15-minute Hikka family. Thank you.
So, thank you Nilkamal, thank you Hiranada, thank you all.
Thank you Devajit, বহুত ধন্যবাদ আমাৰ আচলতে আৰু এখন মানে এইটো অনুষ্ঠান এটা আৰম্ভ হ'ব মানে একে 8:30 অলপ দেৰিতে গতিকে চাগে লগ আউট কৰিব